So hello and welcome to this tutorial. Today we're going to be talking about how we compare respective melting points and boiling points of different substances. But before we start, it's really important to understand what's occurring when we discuss these changes of state. So if we take a look at a molecule, this is going to represent a molecule of methane. We have one carbon and one hydrogen. We have to remember that there are intramolecular forces here. That is, there's a covalent bond that exists between the central carbon and the peripheral hydrogen. When something boils or when it melts, these bonds are not broken. It stays as methane. However, there is a force that exists between these two molecules, and that is what we refer to as an intermolecular force, a force between molecules. These are the forces that are overcome when these covalently bonded molecules change state. That is, when they either melt from a solid into a liquid or when they boil or evaporate from a liquid into a gas. And when we talk about the amount of energy that it takes to overcome these forces, it's going to relate to how strong these forces are that are keeping these particular molecules together and the amount of energy that these molecules have. When we talk about energy, we're talking about temperature, the average kinetic energy of these particles. So the faster these particles are moving, the higher the temperature, and the more likely it is that they're going to be able to overcome these forces. When we think about a solid being together, we have to overcome the forces that are then going to change into a liquid, give it a little bit more motion, and as we have more kinetic energy or provide more kinetic energy by adding heat, the temperature of this substance increases and the particles get more and more energy and eventually have enough energy to overcome the attractive forces between the molecules, those intermolecular forces, and as a result, they can evaporate and turn into a gas. Now that's the case for a covalently bonded molecule, but let's take a look very quickly at an ionic compound. This is a crystal lattice that represents the structure of, let's say, a salt like sodium chloride, table salt, where the green spheres represent the chloride ions and the gray spheres represent the sodium ions. If we were to melt this substance, we would have to overcome intramolecular forces, ionic bonds that exist within the compound. So as a result, there's a lot more energy, on average, that it would take to melt something like this as opposed to a relatively simple molecule, say like methane. Now we will learn that these forces are dependent on a number of factors, and there are some molecular compounds, even some nonpolar ones, that are going to have higher melting points and boiling points than some ionic compounds. But what we're going to look at is the general trend in melting points and boiling points for relatively simple molecules. So the first one we're going to take a look at here is a comparison of methane and chloromethane. So the only difference between these two molecules is that one of the hydrogens has been replaced by, or has in place of that hydrogen, a chlorine. And when we take a look at how we draw these two things, there is our molecule of methane, and there is our molecule of chloromethane. So these are our three-dimensional structures represented in a two-dimensional plane. Now we first have to establish whether or not these molecules are polar. The bonds are polar. The electronegativity of carbon is 2.5 and the electronegativity of hydrogen is 2.1, at least on your periodic tables. So this bond is polar towards the central carbon. Similarly, in this compound, the chloromethane, we have all of the bond dipoles moving towards the carbon, and chlorine, which has an electronegativity of 3, has a bond dipole moving towards it. So overall, if we are going to present a molecular dipole here, we have to keep in mind that the individual bond dipoles from the hydrogens are moving towards the central carbon, and that this bond dipole is moving towards the peripheral chlorine. So as a result, the overall dipole for this molecule could be represented like this, and we would say that this molecule is polar. So with this molecule being polar, this molecule having all bond dipoles, but they effectively cancel each other out. We run into some issues with a three-dimensional structure being represented in a two-dimensional plane, but if we look at it, this molecule is symmetrical. So a tetrahedral molecule like this is going to have all of these bond dipoles cancel out. This means that the only forces here are dispersion, while over here we have dipole-dipole. So we have dispersion forces for this, and I should note that we have dispersion forces for everything. Anything that has electrons has dispersion forces. But this will only have dispersion forces. This will have dispersion and dipole-dipole interactions. As a result, there are stronger intermolecular forces here than there are here. It's going to require more energy to overcome those intermolecular forces, and the chloromethane, as a result, will have a higher boiling point than will the methane. Now, if we bring water in to compare it to this particular structure, the chloromethane, we can illustrate water in a bent or angular configuration. And we can see that it does have two lone pairs of electrons, but more than that, it's got a hydrogen bound to a highly electronegative element, the fluorine, oxygen, or nitrogen. In this case, obviously, it's oxygen. And so this is a candidate for hydrogen bonding. The polarity moving towards the central oxygen, there is an extremely large dipole relative to the size of the molecule moving towards the oxygen. So as a result, there's a special class of dipole-dipole interactions which we've talked about called hydrogen bonding. So the hydrogen bonds that exist in water are significantly greater than the dipole-dipole interactions of the chloromethane, and as a result, it's going to take more energy to separate the attractive forces of adjacent water molecules, and water is going to have a much higher boiling point than the chloromethane will. Now I'm going to compare the boiling point of water to the boiling point of hydrogen peroxide. Now we can see here that hydrogen peroxide and water look very similar, except that hydrogen peroxide has one more oxygen than does the water. We have a similar type polarity in that the bonds of the oxygen and the hydrogen are going to be polar towards the oxygen, so the overall molecular polarity is going to be toward the two oxygen. Now there are a couple of factors here. The dispersion force on the hydrogen peroxide will be a little bit larger than the oxygen because it does have more electrons because of that additional oxygen. But we have to be aware of the hydrogen bonding sites here. There are two more hydrogen bonding sites in the hydrogen peroxide than there are in water. So the hydrogen bonds exist between the hydrogen, being slightly positive, and neighboring lone pairs of the oxygen. And so for each water molecule, you're going to have one hydrogen attracted to one of the lone pairs of a neighboring oxygen. Over here, though, in hydrogen peroxide, we have two additional lone pairs over the water molecule. So there's a greater ability of the hydrogen peroxide to accept hydrogen bonding because of that additional oxygen and those two additional lone pairs. So as a result, the hydrogen peroxide has a larger boiling point than does the water. The last one that I want to talk about is going to be a comparison to water, and I don't have a molecule for it, but if we take a look at this structure represents a large hydrocarbon molecule, which we refer to as octane. Now, octane has only carbon-hydrogen bonds. It is a nonpolar molecule. All hydrocarbons are nonpolar. However, if we look up their boiling points, we will see that octane actually has a higher boiling point than water does, despite the fact that octane only has dispersion forces, and water has not only dispersion forces, but hydrogen bonding as well. However, if we take a look at the number of electrons and the size of the molecule, we will see that it is significantly larger and has significantly more electrons. Therefore, its dispersion force is so great that it actually is greater than the attractive force of water molecules for one another, even with their hydrogen bonding. For my students, I like to compare it to little hooks and loops of Velcro. When we look at Velcro, we can see that one little hook and loop isn't really going to be that difficult to overcome, but when we have many hooks and loops, even though individually they're not very strong, collectively they are. And because of the length and shape of this molecule, it's linear, it's easily stackable. We have a large contact area where those dispersion forces can come in contact with neighboring molecules. And so if we have a really large dispersive force, it can be greater than some of the hydrogen bonding that we see in molecules like water. So when we take a look at the different molecules to try and see whether or not we have something with a higher melting point or a boiling point, what you should be considering is the following. First, what is the overall three-dimensional geometry of that molecule? Second, what are the individual bond dipoles of that molecule? Third, what is the overall molecular polarity of that molecule? And finally, how did the strength of each of those forces that are keeping the molecules together, that is the relative strength of the intermolecular forces, how do they relate to the intermolecular forces of the other molecule? And if we find that they are greater, then it makes sense that it's going to take more energy, that is a higher temperature, to overcome those forces, and therefore we're going to have a higher melting point or boiling point. Sometimes you will get the odd one thrown in. That doesn't necessarily seem like it should make sense, but keep in mind if you come across something that has a higher melting point or boiling point, even though the forces appear that they should be weaker, take into consideration, in the case of a large molecule, the overall dispersive force, because sometimes it can be accounted for if we think about the hooks and loops of the Velcro. So hopefully after watching this video, you have a little better understanding of how we can compare the relative intermolecular forces and their strengths, and how those strengths relate to the melting point, or in this case, boiling point, of these individual compounds. Thanks for watching.